Bom dia a todos que estão aqui nos assistindo no canal do YouTube da Sociedade Brasileira de Hidrografia. Vamos começar em breve a palestra, né, do engenheiro Jens Lowag, da Innomar, na Alemanha. Né? E a palestra se chama Shallow QA Investigations with Innomar Parametric Multi-Transducer System. O Jens, ele é formado, né, na Universidade de Stock, na Alemanha, é cofundador da empresa Innomar Techonogie, né, e desenvolve softwares, operador de campo, geofísica e projetos atualmente. Desde 2021, ele é o presidente da Innomar Technology. Jens, I would like to thank you very much for your presentation. We can start it right now. After you finish, we'll come up with the questions.
Okay, thank you very much, Arthur. It's a great honor for me to be here and to present Innomar and the technology and the products we have built around this. I will give a presentation today about the bottom investigation with parametric multi-transducer systems. So I will firstly introduce you briefly to the technology behind, to the product and its properties, and then I will show you some examples of the results, and also briefly 2 case studies about the application of this technology. So let me firstly introduce Innomar. Just a few words. Innomar was founded in 1997 by a small group of scientists and engineers as a spin-off company out of the University of Rostock. So we were working in an underwater research group for acoustics and have developed various equipment in the field of underwater acoustics, sub-bottom profilers, fishery equipment, etc. And we had a 3-year research project where we developed nonlinear systems based on a parametric effect. And after that, we decided to commercialize this and develop a product out of this technique. So we set it in Rostock, that's in the north of Germany, located on the Baltic coast, a harbor town north of Germany. And over the time, we developed a full product line of sub-bottom profiling systems from very shallow waters, very portable systems, up to full ocean depth systems for ocean-going vessels. So the systems are sold worldwide to a variety of clients, including industry, science, authorities, etc. So now we are a company of 28 employees with a very strong technical base, more than half of it being engineers and technicians, and we continuously develop our products to serve the applications and to serve the market. What does it mean? Parametric acoustics. It's all based on a physical effect we use. Traditionally, sound waves are normal pressure waves traveling in a medium as sinus waves, but there are nonlinearities in the sound propagation if the pressure is very high, because the velocity of the sound wave depends on the pressure, and if you apply a very high sound pressure, the wave crest will travel faster than the troughs, and this will cause a distortion of the sound wave. So it's coming out of this sinusoidal form, into a more shock wave like form, and as a consequence, the spectrum changes in the medium. So you can see this here on the screen, left side, the normal sound wave, for an example, with a frequency around 100 kilohertz. But if you get a distortion, the harmonics will appear in the spectrum. So if you combine now during transmission two frequencies close together, you will get, of course, a distortion for both primary waves. But you will also get then an intermodulation, and you get new frequencies appearing in the spectrum. So the difference frequency based on our two primaries, if we stick with our 100 kilohertz example here, let's say transmitting a 95 and a 105 kilohertz, will result also in a part of the difference being 10 kilohertz. Of course, the harmonics and mixtures remain a spectrum, but for our purpose, we are using the difference frequency, which is a low frequency. So why is it worth to use this effect? As you can see, the directivity pattern on the left side, so the two primaries, only in the primary beam, you have enough sound pressure for the development of that low frequency. So the low frequency has, as a consequence, the same narrow beam width as the primary frequency, and the directivity is flat outside. So there are no side lobes developed for the low frequency, and the sound beam itself is very narrow. As a result, you get, of course, a very small acoustical footprint, and this results then in turn in a very high lateral resolution. So to translate that, with a very small transducer, since our primary transmitted frequencies are high frequencies, you can create a system with a low frequency narrow sound beam. The plot here would also show the directivity of a directly transmitted low frequency, the blue curve, in this case a 10 kilohertz. So it's a very wide sound beam with a large footprint and side lobes present. Additionally to that beneficial directivity for the low frequency, we also transmit very short sound pulses. So the resulting low frequency has no ringing. That means the vertical resolution is also very high, and you can work in very shallow water. So in fact, you can transmit a single cycle of your desired frequency and achieve a very high vertical resolution. So with a very high dynamic range, you get, of course, also very high quality and high contrast data, which aids the processing. For very high low frequency sound level, of course, you need to provide a high primary source level, and that was the difficulty during the development. So you need advanced electronics and advanced transducer design to create that source level in order to apply this nonlinear effect and get useful source levels for the low frequency sound. In practice, it has the consequence of a very high vertical resolution, and this is demonstrated here in a study from University of Ghent, which compared linear and parametric systems. So the top seismic section, it's all the same area, shows the parametric system. The sections below are from a boomer system, from a pinger system, which suffers a lot from the ringing and cannot really resolve anything useful in a very shallow water, and a second boomer system, more lower frequency. But it's clearly seen that the achievement in resolution is significant. So based on this technology, Innomar has developed a full product line of sub-bottom profiling systems, starting from shallow water systems, very portable for any boat of opportunity, even down to small rubber boats, whatever you can imagine. Then high power systems where we increase the transducer sizes to achieve higher source levels and higher penetration. Those systems are also beam stabilized, actively stabilized. So that means in combination with a motion sensor, the sound beam is steered in real time vertically towards the seabed to get maximum reflection energy from your seabed layers. The last few years, we have seen an increase in the demand for autonomy. Autonomous vehicles are developed everywhere, and we have adopted our products to this specific platform with smaller form factors and to make the integration into small-scaled vehicles with restricted payloads more easy and more simplified. Also with remote interfaces, so you can actually control from remote the systems and also monitor the data remotely. We also developed a specific group of products which we call multi-transducer systems. The purpose here is to have a higher data density and to be able to create 3D data sets to map and visualize buried features and buried structures in high resolution laterally and vertically. Innomar also develops their own software, so all systems come with an online acquisition software, with a ZY converter, remote interface, but we have also developed a processing software dedicated to the Innomar systems. However, users are free to choose whatever processing platform they like or they are used to. So with the industry compatible ZY format, you can use any seismic processing software to process the data. So the multi-transducer systems we have developed, there are two versions of it. One is called Quattro system, the other one is six-pack system. You see a picture here with a bow-mounted six-pack transducer. The system itself needs auxiliary equipment. So you need a high-precision positioning system and a motion sensor and a true heading sensor in order to measure the orientation of the transducer array in this 3D space, because you want to combine multiple survey lines into a single 3D cube. So you need to be aware of any deviations from the horizontal and also from the forward direction to measure the points in the 3D space. So both systems operate on primary frequencies around 100 kilohertz. The low frequencies, the difference frequency, are user adjustable, and you have the range between 4 and 15 kilohertz. So the choice of frequency depends on the application, what penetration is desired, what resolution is desired. So there's always a trade-off. So more penetration means you choose lower frequency, higher resolution, you choose higher frequencies. Seabed penetration depends, of course, on the sediments, up to 50 meter for the Quattro system, also depending on the grouping of the transducers, up to 60 for the six-pack system. The beam width for an individual transducer is plus minus 2.5 degrees, so it's very narrow. And this line arrangement of transducers is only possible because of this narrow beam. So we are continuously developing those systems. The first releases have been made in 2015 and 2017. The systems on the market right now are models from 2022, but there's ongoing development to improve the systems right now. There's a flexibility in arranging the individual transducers, which has an influence on the point density, but also on the penetration. So for more deeper waters, it is possible to group transducers. You reduce the amount of channels, but you may increase the penetration. So the various arrangements are listed here. You can also separate the transducers. Every transducer has an individual cable, so that means you are free to arrange. For example, for wider mapping of an area, it might be beneficial to increase the spacing, for example, mounting transducers on the left side and on the right side of the vessel, just in order to reduce the amount of survey lines compared to a single beam system. It is also possible to combine all transducers into a square array or 2x3 transducers. This mode will bring the system into a normal single beam system. So that's then not meant for 3D applications, but you have a single beam system with a very high sound pressure compared to our high power systems. So let's have a look at some examples. This is a survey we did with a Quattro system from a German archaeological site from the Viking area. It is surveyed with a number of lines, in this case 40 meter by 250 meter. So you have to do parallel lines in order to achieve coverage. Once you have surveyed the parallel lines, dedicated gridding software will compute a regular grid out of the irregularly distributed data points. And such grid can then be visualized in a 3D software in order to apply time slices and to remove certain parts of the volume to make buried features visible. So in this particular example, horizontal time slice is used to remove the first meter of sediment and to look inside this volume. And you clearly see a Viking structure made from wood. It's a protection wall at the entrance of an old Viking harbor with wooden crates. This was not possible before, when the scientists were just using single beam systems. You get small individual reflectors, but this gives a much more clear representation of the buried features. A similar archaeological example from the coast of Belgium, near the town of Oostende, a site with old Roman and medieval structures used for peat extraction and salt production. In the 70s, some large breakwaters were built, so the site nowadays is fully covered by 1 to 2 meter sand. It is not exposed anymore. This old photograph is from the 1970s after a storm event where some of these features were exposed. We surveyed this also with a single day. It's quite difficult. It's located in the intertidal zone. It shows several features and structures below the seabed. Next page will show you a correlation between some of the old photos and features we see at the different levels, depth levels of time slices. Yeah, it's quite striking how they correlate in their morphology. Yeah, a classical target for an archaeologist would be a shipwreck. So this is a buried shipwreck in shallow water, just 1.5 meter water depths in the sediment. The outline of that shipwreck is clearly seen. The correlating 2D section is on the right-hand side. Another shipwreck, also from shallow water, also in Germany, an old wreck from 12th century, a small site which can be surveyed in 1 to 2 hours and then transferred into a grid, a regular grid, and visualized. On the next slide, we will see a short video showing that volume and how the time slice is moving down, removing the sediments and revealing the wreck structure. So there's a small excavation pit in the center. There's a little gap because there was a buoy placed for the marking of that wreck, but I think it's quite clear. The purpose here was to define the dimensions of that shipwreck and to prove that it's a fully buried wreck, so no excavation work had to be done to remove it for protection. Yeah, another site from Poland with a crashed airplane. You see the seabed representation and 40 centimeter below seabed with some debris, 2 pipelines, and a lot of markings from vessels, sailing ships, etc. in that shallow water north of Poland. One of the applications is also the detection of UXO. This is an example from a test site in a Navy port in Germany with some test mines placed below the seabed. Left side, a vertical section, and below that is a time slice at the depth level of one of the mines. So all these targets were detected during these trials. Difficulties here, it's a slope on the quay wall, so it was not easy to survey, and there are a lot of other waste in that harbor basin. Another classical example, detection of pipelines, a small corridor in a river. You see the river channel, and on the right-hand side is the river bank. So there's a shallow part. The top 3D volume is showing the seabed, so there's no sign of any pipeline. The volume below is with a time slice applied at 60 centimeter below riverbed, and you see the pipeline reflection, but also the outflow from the end of the pipeline. It was a water pipeline which is not in use anymore. So the morphology of the sediments caused by these water flows. I will show you now some 2 case studies in more detail. One is a comparison between a traditional survey of pipelines in cross-sectional mode. This survey was realized end of 2024 in Portland, US. Columbia River, 750-meter wide river, and some national gas pipelines are crossing the river at that location. These are 14-inch and 16-inch pipelines, and they are buried down to 4 meters below riverbed. The material is sand. You can clearly see the sand ripples on top of the seabed. There's quite some significant current in that river as well. So the left picture shows the mounting of an Innomar medium transducer on a small survey vessel with an over-the-side pole. So there was a quick multi-beam survey above the site, and then we did a number of cross sections along the river, crossing the pipelines. A 2D section on the top shows the distinct hyperbolas. There's a pair of pipelines in that section with about 4 meters below riverbed. And what you would do usually is to pick the hyperbolas as the pipeline location. So you have depth of burial and location of the pipelines. Just for a nice picture, you see diffusion of multi-beam pipeline and seismic section as a fence diagram in that picture on the lower right. The same site we surveyed a few weeks later with the Innomar 6-pack system, but this time the survey was arranged along track the pipelines. So a number of lines, in this case we made 13 lines, a small corridor. You see again the transducer mounted on a small survey boat, the 6 transducers side by side. And the final results, the top is a 2D section from a place where we are almost on top of the pipeline. So you can already recognize the reflection from the pipeline in the 2D section. And on the bottom, you see the gridded volume with the pipeline reflector for the entire crossing of this gas pipeline. The second case study I like to present is from a marine bay in the northeast of Poland on the Baltic coast. It's from a marine archaeological site. It's an early medieval harbor in shallow waters between 1 and 3 meter water depths. There are several phases of harbor development. So at the site, there's a lot of harbor structures, wooden posts, etc., but also a few shipwrecks located. And we surveyed the area in a few regions of interest for the archaeologists within Innomar Quattro system. You see the installation. It's very easy to deploy the system on a bow mount, 4 transducers. It's a fully portable system. So the map shows the bathymetry. The system will also acquire the 100 kHz primary channel. That means you have at the same time a bathymetric data set you can process and use for normal bathymetry map. When you look in the 3D volumes, it's of course a gridded cube transformed from the irregularly distributed points. So we have rendered here 12.5 by 12.5 centimeter laterally and 1 centimeter vertically and visualized. So now the map shows a time slice through the area. And first, what you recognize is the old paleo channel of that local Plutnitsa river. But there are a lot of other features in that area, and it's still an ongoing investigation of that important archaeological site. Additionally, one cross-section is shown. As you see, the seabed is very shallow, 2-meter water depths here. There's some vegetation on top of the seabed and a significant reflector, about 1 to 1.5 meters below seabed. The paleo channel you can see cutting into that paleo surface. Yeah, we will see some more of the surface later. For the in the area, we also have recognized a new shipwreck. The 4 time slices are at increasing depths. So the upper left corner, number or time slice A, is actually in the border column. So you see many wooden posts sticking out of the seabed from former harbor structures. When you come more close to the seabed, you will also recognize several lateral features. These are wooden posts at the seabed, laying flat at the seabed. If you come deeper, you will recognize the outline of a shipwreck, the one we have seen before. And you will also see a high amplitude patch, which is the reflector from some sediments resting on the paleo surface. And this is actually the outline of the former harbor basin. So you see the same in this vertical section between A and B. First the wreck with this typical shape, the paleo surface, and then on top between 50 and maybe 70 centimeters of sediments deposited during the period of activity of that medieval harbor. When you digitize, or we have also digitized the paleo surface in certain area, and you see some additional features here. Circular pockmarks were identified. They are related to groundwater discharge processes in the area, but there are also irregular hollows which are part of the former paleo landscape. It is a former wetland environment which was flooded during the last Holocene transgression when the area was transformed into a marine bay. So to have an outlook for the system and our development plans, right now there are 2 main limitations. The system we have is a vessel-based, so it operates only from ship or boat. And that means even with the parametric narrow beam, the operational water depths is limited to maximum 20 meters. The second limitation we have right now is the swath width, which is maximum 2.5 meter if we want to make 3D volumes like we have seen in the examples before. For these 2 reasons, we are currently developing the system and will make a subsea version of that product. That means we have to produce depth-rated transducers and an electronics pod, which is the more easy part, I would say. But we will also extend the system with a new multi-channel receiver, so we can increase the swath and can also look left and right of the actual transducer array. So we hope that we can have good progress in the near future, and yeah, will make this product even better. Okay, I hope I could give a good introduction into this product and this application, and I am ready for questions.
Hi, Jens. Thank you very much for your presentation. Very interesting, your system. Unbelievable resolution that you're getting with these 3D seismic cubes. My first question is it only achievable when you use the multi-transducer system, right?
Now, theoretically, you could do similar work with a single transducer system, but then you need much more time, and you lose a little bit the coherence in your data set. Because if you have a fixed array with pre-aligned transducers for a single swath, you get very coherent data points for that single run. And if you use only single transducer lines and combine all those lines, yeah, your data is not as coherent as what you can get with the line. But in theory, you could do it with a single beam system, but yeah, at the cost of time.
Yeah, you will need more lines also, no?
Yes, right.
Okay. Another question that we have here, you have shallow and deep water systems.
Yes.
So the parametric technology, is there any difference when you're working on, you gave a lot of examples about shallow water systems, very shallow water systems.
Yes.
But if you go to deep water system, is there any difference on the advantages of the technology?
Generally not. For the deep water systems, we have to change the frequencies. So the parametric effect will also appear at other frequency ranges. The systems we have seen here, they were using 100 kilohertz primary frequencies. If we come to deep water systems, for example, we have a 6,000 meter system, then we have primary frequencies around 36 kilohertz. So as a consequence, also the low frequencies will be lower. No? Let's say if we make frequencies 34 and 38, then we create a 4 kilohertz. But again, we have this parametric effect, and we get a very narrow beam for this low frequency. Of course, the transducer will be larger because our primaries are also lower, and in order to create a very narrow beam, you have to increase your transducer size. No? But generally, the same principle applies, and the same advantages will apply.
So the beam angle will be the same for 4 kilohertz if you use hundreds of kilohertz in the transducer or 30 kilohertz?
Now, the beam width depends only on the transducer size and the primary frequency, the ones which you are transmitting. So for the deep water system, as an example, our 6,000 meter system has a transducer size of 90 by 90 centimeter and will also create plus minus 1.5 degree beam. And that is then the same beam width for the parametric frequency, independent if we choose 3, 4, 5, or 6 kilohertz as our secondary.
Mm-hmm. We have one last question here. For these wind farm, offshore wind farm projects, are you using the single system, the single transducer system, or the multi-transducer system?
Yeah, for most of the wind farm projects where we are involved or what our clients are performing, the mostly used system is our Innomar medium system, a high power system, a single beam system. So that is used first due to its portability, but also due to its performance regarding penetration. The resolution is the same as for the portable shallow water systems because it uses also 100 kilohertz. Source level is higher because the transducer is a little bit larger. but then it's used for site investigation, for the route surveys, to map the morphology, to determine the trenching for the cables, for the development of the wind farms. And also, once a wind farm is built, it is also used for the detection of the cables laid. So depth of burial surveys are used, but then mostly in the traditional way of cross sections, because the water depths will be more than 24 meters.
Well, so far we have not other questions. I would like to thank you, Jens, for the presentation. Very interesting. Your system is not very used here in Brazil, so I don't know how many companies have them here. But I know it. I have worked with an Italian company a couple of years ago here in Brazil. I think it's a very good system. Thank you very much for your time. And in behalf of the Brazilian Hydrographic Society, I want to thank you, and maybe in another occasion we will return. Thank you very much.
Thank you all very much. It was a great honor for me. Thank you.
Thank you. Bye.
Bye.